So when we talk about electrochemistry, primarily relates to two different forms of energy. You have electrical energy and you have chemical energy. Chemical energy is the potential energy stored in chemical bonds, ionic bonds, covalent bonds to be energy of the chemicals. So when you're like any device that you're using, or the process in which you're converting electrical energy to chemical energy would be called, what do you call when you use electricity so that a chemical reaction can take place? So this is called electrolysis or an electrolytic process. So when you're converting electrical energy into chemical energy, so this is your electrolysis, electroplating. You're using electrical energy and converting, like using that to bring about a chemical change, altering the chemical energy. So electrolysis. So that's an electrolytic process. And the devices, you call that an electrolytic cell, where you use two electrodes connected to a battery, and then you have an electrolyte in the container, that whole setup. And the other way around, when you're using chemical energy in order to generate electrical energy. So when the change is the other way around in this direction, that would be called
electrochemical.
This is electrochemical, yes. So the device is called electrochemical cell. This is an electrochemical process. So this is electrochemical. Electrolytic is when you're using electrical energy. Okay. So first part we'll be dealing with electrochemical processes. All the terms, phenomenon related to this. And then finally, we'll look at electrolytic changes, like how much current is required in order to get so much of a metal, the stoichiometry and all of that. Okay. So this is what we'll be focusing on, major part of the chapter. Okay. So the simplest form of using chemicals in order to bring about electricity, you can do it in the form of a Daniell cell. What is a Daniell cell?
Zinc and copper.
So I'll just take like some zinc in my right hand, copper in my left hand, and then I have a Daniell cell.
Yeah.
Acha? Okay, source some zinc.
And salt bridge.
Electrolytes are very much required for this process, you guys. Without electrolytes, electrons nahi hote. So you have zinc and copper, yes. So where you use the zinc electrode, you fill it up with a zinc solution, zinc ka salt solution. Something like zinc sulfate, zinc nitrate, UVM. And where you use the copper electrode, I use orange for this. You're gonna fill it up with copper ka solvent. So this would be.
So like Daniell cell, we can like just make it in the lab or something, because otherwise in a battery we can, we need to buy it, but like Daniell cell is just solution with zinc and copper rods and a salt.
That's it. This is Daniell cell mainly application is to study how, like Daniell cell is specifically for zinc and copper ka pairing. Lot of studies and you can do it with respect to this. But this sort of a setup you'll use to study, okay, oxidation potential kitna hai, reduction potential kitna hai, which is more effective, how much this thing. So this sort of a
that would be, sorry. Yeah, continue.
Yeah, so this sort of a setup is mainly for study and analysis that you do in the laboratory.
I forgot my question.
When you remember it. Okay. So when you just do it, like isme
I remember it. This is like the reduction potential and oxidation potential, like you said, it's used to find that out. So that would be specific only for zinc and copper, right?
No, like any element has an oxidation potential or a reduction potential associated.
No, but using this, we would only be able to find out for zinc and copper, right?
If you use zinc and copper, you will find out for zinc and copper.
So Daniel cell is used to study oxidation and reduction potentials, but using this particular cell, you'll only be able to find out zinc and copper oxidation and reduction.
Yeah, the specific thing. But I'm talking about the setup, like taking a electrolyte and the pure metal pairing and connecting it with a wire and voltmeter, like that whole setup. Okay, so when you leave it alone yahan pe, this solution is going to consist of zinc ions and the negative ions, the anions. Like if you took zinc sulfate, you'll have sulfate anions, nitrate anions. That doesn't matter right now. So we have zinc ions from the solution, and zinc being a metal, there's there's a little bit of equilibrium established where metal electrodes say you have zinc getting converted to zinc 2 plus. Electrons say extra matlab zinc 2 plus will take those electrons, become zinc metal, like all of that, they have their own process established there. Same in the case of copper. You have copper atoms here, and in the solution you have Cu2 plus ions. Yahan pe you have like Cu atoms here. We just put it out there that you have zinc atoms and zinc 2 plus ions. Okay. When you connect them, when you connect both these electrodes using a wire, and let's just connect a voltmeter to take the measurements. So what happens is zinc is a lot more electropositive than copper. Like reactivity series maybe they can, like when you have zinc and copper put together, zinc is the one that usually prefers undergoing oxidation, and copper is the one that usually prefers, like, it will also be oxidized, but in the presence of zinc, this is going to take up those electrons and form copper. So when zinc is undergoing oxidation, when this is the thing dominating here, you'll have like excess of electrons over here. And once you attach the connecting wire, electrons have an outlet. They will flow through these because the copper 2 plus ions from the solution are ready to take the electrons to get reduced to copper. So that sort of a flow is established, but it only happens to some extent. Like even the copper from this is just as capable of releasing electrons, form Cu2 plus, and then give the electrons back. Like there's no equilibrium as such, there's no reaction, nothing happens at the moment. But when you complete the circuit, when you provide these electrons a specific pathway that they can continuously follow, so that comes in the form of a salt bridge. It is literally a bridge made out of some salt so that there can be some sort of an ion exchange taking place between both. So salt bridges are made up of, you have a salt mixed in jelly, or like in some cases, like if it's a homegrown thing, you can immerse like a paper, not a cloth towel or a napkin in a salt solution, like make it full of the salt solution, and then use that as the salt bridge. So usually the point is that you have something to hold the ions of the salt here, and you have something that enables the exchange of ions with the solution. The sole purpose of the salt bridge is to complete the circuit so that the charges are able to move continuously from one side to the other. So when you do that, you notice that the volt, like there is flow of electrons, there's a potential being created, like excess of electrons produced over here, and the electrons are taken up by the copper as they flow. So you have like a positive charge created over here. So one side has more electrons, the other side has less electrons. There's a potential created across both ends, electric potential. That is measured across the that is measured on the voltmeter. Yeah. So that basically completes the cell. And then you use a wire. You can take this electricity to, I don't know, put a bulb here, use it for whatever purpose. Okay. So that is the thing. Because zinc is oxidized and electrons are produced here, this becomes the negative electrode. So this will be the, yeah, so this forms the oxidation half because oxidation is taking place. And यहाँ पे, because copper is being reduced by taking up the electrons, this forms the reduction half. Okay. What else do we have here? So how much electricity is produced, all of that depends on the concentration, the availability of zinc ions and copper ions here. If we take standard concentrations, if the concentration of Zn2 plus is equal to concentration of the copper Cu2 plus is equal to 1 mole per dm cube, then the EMF that was produced between both was measured to be 1.1 volts. So this is like the basic setup of Daniell cell. Why is it a cell? Why is there flow of electricity? It's because of the difference between the what do you call it? Tendency of getting oxidized or reduced between zinc and copper, because there's a difference between both of them. Zinc can get more easily oxidized compared to copper. So this is the one that's going to release electrons at a much faster rate. Like copper is just, copper also can produce electrons, but because it's at a lower rate, this is going to dominate in the oxidation. So you have more electrons produced here, which starts flowing towards copper, where copper ions from the solution absorb and see, if copper Cu2 plus is absorbing the electrons, there's a lot of negatively charged ions ka concentration increases over here. You need to sort of like keep that under control. So that is what the salt bridge is for. It forms a bridge between both. It enables ion exchange. Enables ion exchange, matlab, through that the charges can keep flowing. The electricity will keep going.
What is above the voltmeter?
Oh, I've just like drawn a rough bulb. So basically, once the current gets going, you can use that to, I don't know, light a bulb or like whatever you use electricity.
Like to indicate if the current is.
Yeah.
And what is that? One what?
This one.
Yeah.
So if you take the concentration of the zinc solvent, copper solvent to be equal to 1 mole per dm cube, like 1 mole per liter, then
Yeah.
the EMF that is produced was measured.
Acha, yeah. I understand.
Yeah.
One mole per liter of what? The whole solution, right?
Concentration of the solution. Yeah.
So molarity.
Yeah. This is the salt bridge.
1 dm cube is 1 liter.
Yeah. Okay. So we'll do something more with this. Suppose you have set up the
Okay.
Daniels.
So the salt bridge maintains equilibrium, right? Like maintains equilibrium between the two solutions, right?
Equilibrium maintains the neutrality.
Neutrality.
Done.
Okay. So suppose, yeah, you have your Daniel cell set up. I'm just gonna draw it very simply. You have two electrodes. Salt bridge. To this circuit, let's say you connect another external battery. Like you have external voltage across the same points. So already the existing potential between these 2 points, because of zinc and copper, because of the half reactions taking place, was established to be 1.1 volts. Standard, like you're taking 1 mole solutions, and yeah, you got like 1.1. If the external EMF, E external, applied is less than 1.1 volt, what do you think will happen to the salt bridge? Not the salt, like to this reaction, the half reactions taking place.
Nothing.
Nothing. Okay, yeah, like
No, it will happen. Something will happen.
Same reaction.
same reaction will happen, yes. But because you have an opposing voltage applied, it will happen. Um, it will be slightly slower. No,
What was that part where if you apply less than 1.1, then it goes from zinc to copper, something like that?
No, that is more than 1.1.
yeah. So if you apply less than 1.1, the same reaction will continue. It'll just happen to a lesser extent. But essentially, yeah, the same half reactions will happen.
And at equal, no reaction.
Yes. So if the external voltage applied is equal to 1.1 volts, then there's going to be no reaction, because whatever electrons are flowing, the other external voltage is like opposing it. So kind of like the front and the back are getting cancelled. Forward and backward will get cancelled. Reaction will happen, but like it'll be to a reduced extent compared to when it's not there. But when you increase it, when the external voltage is greater than 1.1 volts, then the reaction will be reversed. In this case, it will be reversed because you're uh, giving a lot of electrons to copper, like in the opposite direction. So, you're giving a lot of electrons to zinc. So it goes in the opposite direction. Zinc starts getting oxidized and zinc starts getting reduced and copper starts getting oxidized. So this is when an external EMF is applied across the same points. So depending on the value of the EMF, you observe all of these. Let me know when you guys are done. We'll start the next. So it's like based on Daniel cell by changing the materials used, changing the concentration, like a lot of rest of all of electrochemistry has been developed. So that's what we'll be getting into now. Done? Okay. Sia, are you done?
Yeah.
Okay. So some terms that we use in this chapter. The first one being electrode potential. What is electrode potential?
Potential of the electrode to.
Perfect. Yes. Potential to do what? Win a Nobel Prize.
Carry out the reaction, like for the reaction to take place.
For the reaction to take place. Specifically, like from now onwards, if we say reaction, it's the oxidation or reduction. The tendency to lose electrons or gain electrons, depending on where it is in the reactivity sequence. Yeah. So electrode potential, it is basically it's the potential it is measured between the electrode and electrolyte interface. So electrode and electrolyte interface. Basically this part of the cell or this part of the cell, depending on what you're looking at. So suppose you have the electrode and then it's surrounded by the electrolyte. So electrolyte may you have uska positive ions. Usually we talk about metals. So it's surrounded by the positive ions. So this particular exchange, so when M plus leaves the electrolyte deposited on the electrode, you like the electrode ends up getting a positive charge. And when the other way, like when like in the case of zinc, when the metal atoms leave the electrode, get dissolved into the solution, then like because there's electrons that it's leaving behind, this ends up getting a negative charge. So again, as I told you, like if you simply have an electrode dipped in an electrolyte, both the processes are taking place simultaneously. So you have metal atoms leaving the electrode, dissolving it into the solution, and electrons get left behind on the electrode. And also the ions from the solution taking the electrons, getting deposited on the metal. So both of them are in equilibrium. So at equilibrium, what's happening here? Are you guys like focusing, following along?
Yeah.
Yeah, sure. Okay. Don't get distracted, guys. Like, okay, but don't get carried away. Yeah. So, depending on the reactivity of the metal, one of these two processes is going to dominate. So, at equilibrium, so how much ever charge is deposited on the metal. So, if the oxidation is happening a lot more, then there's going to be negative charge on the metal. So, this is going to result in a negative charge on the electrode. And if this is the process happening, like metal ions getting deposited on this, you're going to have positive charge on the electrode. So at equilibrium, whatever is the result, like whatever is the resulting charge, that's what is termed as the electrode potential. So at equilibrium, the potential difference that you get because of the charge being deposited.
So in terms of observation, what you would see at equilibrium is how much ever of the metal is getting reduced, the same amount of deposition is happening on the other electron.
Yeah. This is electrode potential. Okay. Now, this can occur at any point of time. It depends on the concentration of the, like, it is equilibrium, right? So, equilibrium by definition, you can control it by manipulating the concentration of the solution of the ions. Increasing the concentration of the solution is going to push it in one direction, decreasing it is going to push it in the other direction. So that is the reason we consider something called standard electrode potential. So this is basically our point of reference for every metal. Like you keep the conditions same, and then you can compare it across different conditions for the same material, or at the same conditions, like say 25 degrees Celsius, 1 atmosphere, this particular concentration may, which one is a better reducing agent or which one is a better oxidizing agent? Zinc, copper, sodium, aluminium, iron, जो भी है. So that's what you use, like standard electrode potential is a point of difference. So this is the electrode potential at one, you take 1 molar concentration. So 1 molar concentration of the electrolyte, like unit concentration. 2 at 1 atmosphere pressure, that's like atmospheric pressure, what standard conditions you have, at 298 Kelvin standard. Okay. So this is what IUPAC has defined. So if you're talking about standard electrode potential of any element, any metal, these are the conditions you're referring to. You're taking 1 molar unit concentration of that salt at 1 atmosphere pressure and 298 Kelvin. Another thing, so whenever you're calculating the standard electrode potential, this always refers to the reduction potential. And if you want the oxidation potential at the same conditions, you just reverse the sign. The value will not change because the conditions are the same. The numerical value will remain the same. But whether you're talking about reduction versus oxidation, whether you're going from M2 plus to M or M to M2 plus, reduction or oxidation, simply the sign will get reversed. Rest of it all remains the same.
But this reduction potential and oxidation potential is only for standard electrode potential, right?
Yeah. No, standard electrode potential matlab by default, if nothing is mentioned, we're talking about the reduction potential.
No, like I'm saying that if these particular conditions are followed, then the electrode potential that we get is the standard electrode potential, right? But otherwise, if you calculate it at other values, so is that is just electrode potential? So
Yeah,
is that
that's just
still
electrode
reduction potential?
Correct.
So that's not reduction potential. That's only electrode potential.
Yeah, it depends on which direction, how you have calculated it. Like again, we said that both the processes are going to take place, right? So
Yeah.
if this tends to dominate, you end up with a negative charge. So
Yeah.
this will refer to the reduction potential, because reduction process is happening.
Okay. So it doesn't necessarily have to be standard electrode potential, right?
No.
Like even electrode potential can be reduction potential.
Yeah.
Yeah.
Reduction or oxidation. But like when you look at a reference value saying such as zinc, the standard electrode potential of zinc is minus 0.7 volts or something like that. So that refers to the reduction potential. So if you want to get the oxidation potential, then it will have to be plus 0.7, whatever the value is.
Wait, can you go back 1 second at what you just wrote?
Huh?
That is loss of electron, right?
Yeah.
So that's oxidation.
Yeah, sorry, I marked the different thing. Increase of oxidation state. This needs to be oxidation. This will be reduction potential. Yeah, this is reduction. This will be oxidation. Yeah. But so reduction potential, like whenever we come across standard electrode potentials, they're always the reduction potential of that particular this thing. So reduction from M, it doesn't have to be 2 plus because we've been seeing copper zinc 2 plus clear, but yeah, positive charge to metal, ion to metal, metal to ion. Okay, what else do we have? Cell potential. Okay. What do you think cell potential refers to? So for a cell, in order to flow, like maintain the flow of electrons, you need something to give the electrons, you need something to take the electrons. So you always need a reduction half and an oxidation half. So a reduction half and an oxidation half put together gives you a cell. So you need a reduction happening and an oxidation happening, which is like when one gives the electrons, the other one takes the electrons, right? So reduction means gaining the electrons, the oxidation is like giving the electrons. So in order to create a cell where there is constant flow of electric current, you need a reduction half plus an oxidation half. You need a combination of both. So that's what cell potential is. So E naught cell, because we're talking about standard. So whenever anything is standard, it's basically represented by this naught on top. Okay. So E naught cell, standard like cell potential, is equal to E naught at cathode minus E naught at anode. Minus because they're in opposite directions. Like whenever you're calculating, अगर एक का reduction है, दूसरे का if you're considering, like it needs to be reduction minus oxidation. Because this is in a reverse process, you add the minus sign so that everything is standardized to a constant. So it's like the electrode potential of the reduction process plus oxidation process. But kyunki we always take like standard electrode potential, oxidation ke liye you need to reverse the sign. So formula mein, that's where you get the minus from, because they're opposite processes. Okay. In other words, the reduction half minus oxidation. So this is an important formula, like you'll get numericals based on this, where you'll be given the reduction potentials of different materials, and you'll be asked, okay, like if there's a cell made from all of these, then what is the EMF of that particular cell? You just have to like subtract the values, you'll get it. So like note down this form, note it down in this format, then you won't have any confusion whether to reverse the sign or keep the sign. So the EMF of a cell is equal to, because we are always using standard values only, so the reduction potential of cathode minus the reduction potential of anode. So you're using reduction potentials, like numerical values are reduction potentials in both the cases, but one is reduction, so you'll retain the value as it is. Dusra is getting oxidized, like copper, zinc copper pair mein copper is getting oxidized, isliye uska numerical value, the sign will get changed. No, zinc is getting oxidized, na? Like copper will remain as it is, zinc is getting oxidized, so uska numerical value, you'll change the sign. Yeah. Let me know when you guys have finished noting. There's less than a minute. We'll continue once this ends. Finish noting. One more thing we forgot. Dono mein se, out of the two halves, which side is cathode, which side is anode?